We're here today for this climate coffee with Torsten. Torsten is working at the Potsdam Institute for Climate Impact Research. He will be talking today about the tipping risks and the mapping of the tipping risks from Arctic ice basins and the global warming. So this talk is funded by several projects in different components. So that's why you see all the logos here underneath. Before I just give the floor to Torsten, just to remind you that the climate coffee, these are like very informal meetings for people to present their results, papers, but also, let's say, invite other people to the discussion that is emerging from this talk, and also maybe to look for collaboration. So this is a way also to discover each other's work. So this is a very, easy format. Use it. It's funded by the European Union, as I said, through different projects, and it's supported by the Danish Meteorological Institute, where I work, and also by the European Climate Research Alliance. Now, before we go further, there is a page on the LinkedIn. You can look this up. This is Climate Coffees, and this is where also you can sign up for events and for being updated about the activities that we propose. This disclaimer is just to... That microphone's open. Okay, I'm muting Daniel. Disclaimer. So the views and opinions you will hear today, they belong to Torsten and also to the people that co-author the paper that will be presented today. They do not reflect necessarily the views and opinions of the European Union, nor of DMI, nor of ECRA. So this is just, for you to understand what we are, let's say, what we are talking about, and also who's responsible for the content. So this is a very standard way to put this kind of framing these activities. Now, housekeeping rules. Check your microphones. I think they're all muted. Only Torsten should have the microphone open. And hopefully people come in with the microphone on mute. You're kindly asked to put your cameras switched off. Andres, I'm muting you. And questions will be taken after the talk. So around 15 minutes, maximum 20, Torsten will be talking. After this, we got another 20 minutes for a Q&A. For this, you can use the chat, or you can raise your hand, and then you can unmute yourself, and then we will reply the questions. You can use the chat also during the talk. So if you would like to share resources and ask questions, but Torsten will ignore the chat until he's through with his presentation. And as usual, we share the recording and we share the presentation as well. And also in the chat, I will paste some resources and references to papers that Torsten has in his presentation, so that you can also find a record of all the different resources. Thanks.
Thank you for having me, and a wonderful morning to everyone joining today this climate coffee. I have my coffee ready here. So this talk today is about tipping dynamics, tipping risks in the Antarctic ice sheet. And this is work not only done by me, but with several people. Of course, important here, Ricarda Winkelmann to mention, but also Julius Gabe, Jonathan Donges, and many more. And it's built on previous work. I will show a little bit of that later as well. I'm not only based at the Potsdam Institute. I'm also working at the newly founded Max Planck Institute of Geoanthropology in Germany. And as I said, this whole work also is a result of previous projects, previous work. So I just listed some logos here as well. So let's dive into tipping. So first of all, tipping research has going on for many years now. And if you consider, for example, the last 25 years, while global mean temperatures have risen quite substantially, at the same time, also the risk levels or the thresholds of tipping points in the Earth system have been adjusted over time. This is what this graphic is supposed to see. So the more we know about tipping dynamics, the lower the thresholds and the risks basically become, or the higher the risks become, basically. And so we know a lot about many tipping elements in the climate system by now. So just this illustration here on the right are only some of it. And we also know that those tipping elements can interact and so on. So there's a whole tipping points in the comparison going on right now. And there's also a framework paper for TIP-MIP in review right now. And it's, I think, also a really good read, because we also provide some terminology here, because tipping has been used in over the years in many different disciplines by now. So if I talk about tipping right now, or tipping dynamics, it's always connected to at least one positive self-amplifying feedback mechanism. So this is one requirement for tipping to occur. That also means there's a threshold, a tipping point, and if this at least one, and if this tipping threshold is hit, then we can observe like a regime shift, an abrupt change in the system. And then again, if you, for example, would change back the parameter, basically that it's, so the system will not go back into the previous state so easily, so that it's often called hard to reverse, or even irreversible. So that's another important term in this context. And if we consider like large scale tipping dynamics, then we often use this term tipping element. And there are, as I said, several in the climate system. So maybe it's good to provide sometimes this kind of definitions. Okay, so feedbacks, I said it's something that's really important when we talk about tipping. So if we consider feedbacks in the Antarctic ice sheet, in a marine ice sheet, which is, for example, partly based, resting on the sea ground. So that's what this illustration shows here. So we have normally also like a triple point, the grounding line between ice, ocean, and bedrock. And this is like a very sensitive, important location for marine ice sheets, because there we can observe, or that has been postulated already many decades ago, the marine ice sheet instability, or short MESI. There are other important positives amplifying feedbacks, for example, the melt elevation feedback, which is important, for example, if we have melting at the surface, and the surface of the ice sheet sees lower elevations and warmer temperatures, this can amplify the melting and the lowering of the ice sheet, basically. So, and there are many more, but which is also very important, there are also a lot of negative feedback, stabilizing feedback. So here's just one in blue. It's one connected to the uplift of the solid Earth and the gravitational pull of the sea level, for example. And there are many more negative feedbacks, which are so important also to highlight, because these are responsible for the resilience of the different Earth system components here. All right. So one study that I would like to mention before I come to the tipping risks is a study on the hysteresis of the Antarctic ice sheet from like 6 years ago right now. It was published in Nature, and mainly work by our PhD candidate Julius Gabe. And so we used the parallel ice sheet model here, and we did a comparably simple experiment. So this is not a projection or something. It's really a model simulation where you start from a pre-industrial state or a present-day state and extremely slowly increase the temperatures so that the ice sheet can adjust to this boundary condition. And typical timescales in ice sheets are something like, many thousand years, sometimes even many 10,000 years. So it takes a long time to reach a stationary state and equilibrium. And you can do that in a really long simulation, and you get something like a quasi-equilibrium trajectory. And this is something I could show here in this little video. So this is the Antarctic ice sheet basically starting from today. And we have almost 60 meters of sea level equivalent ice volume here. And then we see already early on at around, this is a parameter down here, the global mean temperature. And we see quite a substantial change at around 2 degrees in this case in the West Antarctic ice sheet. So this is really what's often discussed in terms of marine ice sheet instability, that we are close to the threshold there. But if we go a little bit further, so we also see a lot of retreat in East Antarctica, in the Filchner catchment, in the Wilkes Basin, now here in the Aurora Basin. And then we see also quite a dip around like 7 degrees of warming. And we can just go on with temperatures incredibly high, right? 10, 11 degrees global mean temperature. So this is really like a more conceptual experiment where we really want to learn about, where are actually thresholds and what kind of feedbacks kick in at which temperature level. So that was this study, and we found this basically like 2 main tipping elements, basically, to say, in the Antarctic ice sheet. So in the West Antarctic, which is really like dominated by the marine ice sheet instability. And then in East Antarctica, also the surface processes, for example, the melt elevation feedback, becomes really relevant at much higher warming levels. Okay, and I mentioned already this term irreversibility. So what we also did, we cooled down the temperatures again. So when we warm up, we kind of followed this trajectory here until all the ice was gone, until 0. But then we could cool down the temperatures again, and we see we have a completely different trajectory, because the buildup of an ice sheet, like it follows a different path, right? There's a path dependency, and you need much colder temperatures to regain as much as ice as we, for example, have today. And so what we did, so from the different temperatures along this trajectory, we kind of branched off simulations. And we ran them for 50,000, sometimes even 100,000 years, to really find this equilibrium state for the different temperatures levels. So these are those triangles here. So you see at some points it's even lower than this trajectory, because it takes a little bit longer time than the forcing rate that we applied. So this simulation, for example, was run for more than 100,000 years. And so this is sometimes not long enough to really reach a full equilibrium. And so in the following, we will use this kind of really steady states for the different temperature levels to have a closer look into it. And this has been done in this more recent paper called Mapping Tipping Risk from Antarctic Ice Sheet Basins Under Global Warming. So this is more like I would call it like a regional disintegration of tipping, and a closer look into the different basins. So we kind of subdivided Antarctica into 18 different drainage basins. Here's what you can see here by those black lines. And what we also see, that the bed topography in many regions, not only West Antarctica, has this bluish colors, which is really bad below sea level. So we also have the subglacial basins in East Antarctica, Wilkes subglacial basin, Aurora, and some other regions over here. And this is important to keep in mind, because if you consider this kind of different temperature levels, you see like very different distributions of the Antarctic ice sheet. So almost ice-free at 10 degrees and something in between for lower temperatures. And we now can, for example, have a look along certain transects in the Antarctic ice sheet. For example, the famous Thwaites Glacier in the Amundsen Sea Basin down here. You see like this reddish colors, which means for already 1 degree of warming, or between 1 and 2 degrees of warming, you lose quite a lot of ice in this region. And this is like a really typical subglacial over-deepened basin here. And then later on, you see those colors here. That's a more gradual retreat. Then we have, for example, here in East Antarctica, the Aurora subglacial basin, the famous Totten Glacier. And you see for a warming until 5 degrees or so, there's almost nothing happening. And then this kind of threshold is hit, and you see a large part of this basin, of the ice of this basin, is basically lost. And what you also can see, like the vertical scaling here, like the ice sheet can be like as thick as like 3 kilometers or so. And what you see here at the ground, this kind of grayish or black colors, this is viscoelastic bed uplift. So this is also a very important component. So if you lose the ice and the load, the solid Earth rebounds, basically. That's also often called glacial isostatic adjustment. And so this can be also of the order of many 100 meters, sometimes even 1 kilometer up. And this also, of course, then can have a stabilizing effect. So a different way of looking at it is to have really this 18 different 18 different basins or drainage basins. And so for each basin, we kind of plotted here in blue dots for each degree of warming basically the ice volume or the sea level rise potential within this basin. So for example, for the Thwaites Glacier, it starts with, around a little bit more than 1.2 meters of ice equivalent sea level. And then we see this immediate drop to almost, so it's losing already almost, 80 centimeters of sea level equivalent after the first degree of warming. And then there's the rest is more this gradual part. We have a lot of, we find something like tipping in, that's a question. So there's very obvious tipping in many of those basins. For example, also here in Filchner, we have actually 2 tipping points at different warming levels. But for many regions, it's rather a gradual retreat. And then at some point, certain feedbacks kick in, right? And that's super interesting to have this closer look into this regions. So we can now order this different basins along the thresholds. So this is like a so-called burning embers diagram, basically. So for example, we find Thwaites and the Cycle Coast area here for quite comparably low tipping points or temperature thresholds. And in this graph above, this is like the total possible sea level rise potential from each basin. So we have basins which more than 10 meters of sea level equivalent, for example, in the Filchner. But for example, Thwaites has more like this 1.2, 1.3. So comparably low impact, but the threshold. Yeah. Right. And if we now combine those two, like the sea level potential, which is basically the potential impact, and the likelihood, like the threshold, how close we are to tipping, then we can also, for example, find this kind of, or illustrate it in this kind of a map. So for example, this balls or the circles basically symbolize the potential impact, like the sea level rise potential. For example, for Thwaites, or for the Amundsen Sea, it's about 1 meter, so quite small ball, but it's really red. So it's so close. We are already so close to tipping, or maybe already in the danger zone. While, for example, in the Totten, the threshold is still some distance, but then if we would hit the threshold, we would get many meters of sea level rise in the long term, right? So that's always that's really the sea level commitment. And what we can do now, what's often done, so if we kind of multiply the likelihood and the impact, we can define something like a risk. So this is really just the first order assessment of risk. And this can be done on a kind of a matrix type illustration. So this is basically like a 2-dimensional matrix here. So the x-axis again is a long-term impact. The y-axis is basically the likelihood, or how close we are to the threshold. And the lower right, for example, would be like the high danger zone. So close, like with a low threshold, but with a high impact. And we find, for example, Thwaites Glacier and Ronnie down here, the lower left. So it has, the threshold is very close, but the impact is, I mean, considerably small. I mean, we're talking still about meters, right? So, but it's comparably small compared to this second category here, up here, Filchner, Amery, and so on. So if we would have global mean temperature rise of about or above 5 or 6 degrees, we would kind of risk to lose those areas in East Antarctica, and this would imply a long-term committed sea level rise of several meters. So this can be really helpful also for identifying what kind of risk zones we actually have in the system of the Antarctic ice sheet. Okay, and just to mention, so we only consider here in this study like degrees of full degrees of change, like 1, 2, 3 degrees, because there are of course a lot of uncertainties involved. So we make a lot of assumptions here, and we discuss this also in the paper that temperature thresholds could be also a little bit shifted regarding these uncertainties, but in most of this kind of sensitivity checks, actually, like the threshold didn't shift by more than 1 degree, which basically tells us that, you know, the qualitative behavior in the different regions, like when certain feedbacks kick in and in which order basically we would risk certain regions to lose or lose a lot of ice in the long term. I think this is something that is really robust in this study. And I just wanted to highlight this. This is not about really comma valued thresholds. It's more like a gain in system understanding here. So it helps a lot in kind of evaluating potential risks also for example, for decision makers. Just to summarize, so this is no sea level projection, this study. It's really a stability analysis in the quite classical sense. So we consider really long-term stationary states here, but we could find out about really how those different different basins are interacting as well. So there's of course a dynamical interaction. So we could find all this kind of more gradual changes, but also this nonlinear thresholds in the different regions. We found multiple tipping thresholds in Antarctica, of course the known ones in West Antarctica, but there are also the subglacial basins in East Antarctica between 2 and 5 degrees, and this more terrestrial, non-marine parts of the East Antarctic ice sheet where, for example, the melt elevation feedback kicks in a lot, similar to, for example, what's important in Greenland for already lower temperature or temperatures. And we provide this kind of first order risk analysis. And for example, we have these 2 categories here, Totten Moscow, Filchner, the Ross East. They have a high risk mainly because of their, high sea level commitment in the long term. But then we of course have Thwaites Pine Island, Cycle Coast regions, the Wilkes subglacial basin, where the threshold is considerably low, where we are close to the threshold. But but then the impact would be on the meter magnitude. That's it from my side. So watch out this paper that has been published earlier this year. And if you have questions or also ideas of how to go on with that, drop me an email. So we are also currently working on this, for example, so I showed in this earlier, for example, we are also investigating the role of the solid earth in this process more in detail right now, and some other processes. But of course, this is still a standalone ice sheet model. So the next step, of course, would be also to really consider this in a more Earth systematic sense, with all the feedbacks between ocean ice, between atmosphere ice, and also solid Earth sea level. But that's it from my side. So I'm really looking forward to questions and discussions.